Hi, my name is Carl Yedor, and I currently work as a predictive modeler for Navy Federal Credit Union in its Fair Lending Division. In addition to my day job in data science, I also write about football from a statistical perspective for Football Outsiders, a website that takes a statistically oriented approach to football analysis. I've been a sports fan my entire life, and when presented with the option to examine the Moneyball dataset for my final project in MSTS 411, I definitely wanted to take advantage of it. After taking an initial look at the dataset, I decided to experiment with the data using multiple unsupervised learning methods. I split the research into two main tasks to answer the motivating questions. First, can we effectively identify similar teams based on their high-level statistical profiles? And second, are there underlying factors that might explain relationships between the potential explanatory variables in a future supervised learning analysis? If so, what characteristics might those factors represent? These two questions provided a framework through which I was able to analyze potential commonalities between different teams in the dataset. For this project, the work broke down into three main steps. First, I'd perform the exploratory data analysis and data preparation work to understand the data and get it ready for analysis. By visualizing correlations between the variables and reviewing different distributions, I was able to identify potential problem areas that needed to be remedied in data preparation before we could begin modeling. The biggest task for data preparation turned out to be handling null values and potentially influential observations. The variable team batting hit by pitch was null for the vast majority of the dataset, so it was not a viable option to be included in the modeling. If the data had been present, I would have been able to add that variable to the analysis, which could have potentially altered the final results. Additionally, there were several columns that had impossible values for certain fields based on my prior understanding of baseball. Some rows were missing values for multiple variables, others were zero and it wouldn't make sense. Some of the values were completely outside a reasonable range in a 162-game baseball season. In one extreme example, there was an observation with over 19,000 strikeouts by its pitchers, which would have averaged out to 119 strikeouts per game. Considering that there are only 27 outs possible in a standard 9-inning baseball game, this observation was clearly an error. In cases like these, I removed the observation from our dataset to avoid compromising data quality. For our data for clustering, I had to scale the data down to a range between 0 and 1 so that certain variables with larger magnitudes would not impact the results too much. For null values in columns other than the hit by pitch column, I imputed the mean and added an indicator variable to the dataset signifying that the value was originally missing. I also added an interaction term between the mean and the indicator variable, and these were used in the cluster analysis but not the factor analysis due to collinearity issues. I also had to remove the team pitching home run variable for the factor analysis due to its very strong correlation with team batting home run, which was almost 0.97. This is a bit of a red flag as well for our data quality, but we have to move forward with the assumption that this is the best data that we have available to us, as there's not much else we could do about it. After completing the data preparation, I moved on to the more interesting parts of this exercise. First, I conducted a principal components analysis on our clean dataset to serve as a point of comparison in our clustering on our dataset. I used a two-component projection of the dataset to feed into the different clustering algorithms after identifying potentially interesting numbers of clusters based on the regular clean dataset. I conducted both a hierarchical clustering analysis and a k-means clustering analysis on our clean dataset, comparing the clustering analysis using the between sum of squares percentage metric across clustering iterations from k equals 3 to 10. After recording the different values of the clustering iterations on the main dataset, I chose multiple different levels where there seemed to be a jump in explainability to test a version of the model on the principal components. I then compared the results and identified the number of clusters that I felt best delineated between groups of teams by weighting the total number of clusters, not wanting to choose too many, while still having a high value for the between sum of squares percentage. Finally, I conducted a factor analysis on the original variables, excluding the aforementioned team pitching home run due to collinearity, and I performed an initial correlation analysis to identify potential sources of multicollinearity within the data. I then ran an exploratory factor analysis for k equals 3 through 7 factors using both orthogonal Varimax rotations and oblique Promax rotations. After identifying the variables that appeared to be associated with each factor for all 10 analysis iterations, I identified what I felt was the iteration that provided the best interpretation for the underlying factors between the explanatory variables. In our clustering section of the assignment, I ran both a hierarchical and k-means clustering analysis for k equals 3 through 10 clusters, and then assessed where there were notable increases in our accuracy metric. For the hierarchical clustering analysis, there were essentially accuracy tiers, where k equals 3, 4, and 5 were on their own tier, 6 and 7 were pretty similar, and then k equals 8 through 10 were similar. For the k-means clustering analysis, we saw tiers of k equals 3 and 4, 5 in its own section, 6 through 9 being pretty similar, and then 10 being a notch above. Given that there seemed to be these accuracy tiers starting at k equals 6 and k equals 8, particularly for the hierarchical clustering analysis, I decided to run iterations of both the hierarchical and k-means clustering models on the principal component projection of the dataset to compare the results. After assessing the accuracy changes for the 3 PCA models in each algorithm, it was clear that the accuracy improved when using the PCA for clustering compared to the original dataset. The best cluster representation of that data was likely the 6 cluster representation because of the trade-off between accuracy and explainability. We saw better results across the board for the hierarchical clustering analysis, which is not exactly surprising given the size of the dataset, though if the dataset were larger, we may have run into some issues with runtime. As a point of comparison for the hierarchical 6 cluster model, I've also included a visualization of the 6 cluster k-means model on the principal components. Based on this distribution, it appears that there are 6 real pockets of observation, though cluster assignments do not exactly match up with what I would have assumed was the case visually. Additionally, cluster analysis assumes that clusters are spherical and of the same size, and with the way these clusters are bunched together, that may or may not be the case. With that in mind, we have to take the results here with a bit of a grain of salt. Some of the clusters shown in the visualization could have been part of an 8-cluster solution. However, these would be potentially overlapping even more, so they may not be the best split of the data. If I were to move forward with an analysis based on these clusters for a supervised purpose, I would likely choose the 6-cluster hierarchical model as my baseline analysis. The clusters were not always perfectly clean, but there were some general similarities between the different teams in the dataset, making this exercise definitely valuable. And we see, especially with k equals 6 for the PCA, that the between sum of square percentage was very high for the hierarchical analysis. For our factor analysis, I was working with fewer variables than we had available to us for the cluster analysis due to the previously mentioned collinearity issues. Still, I was able to construct several different factor analysis models that represented some underlying factors for the different explanatory variables in the dataset, which is good because in factor analysis we assume that there will be underlying factors that can explain relationships between a group of potential predictor variables. The positive and negative associations did not vary significantly across the different factor models and rotation styles. As more factors were added, additional characteristics became present, but the variables that displayed stronger associations, which I considered to exceed 0.4 in factor loadings, were more or less the same. After iterating through factor analyses for 3 through 7 factors using both a Varimax and a Promax rotation, the analysis that produced the best factor interpretation in my subjective opinion, admittedly, was the iteration with 5 factors using a Varimax rotation. The loadings for this analysis are displayed in the table on the left alongside my general interpretation of these factors. After cross-referencing with the variables in the dataset, I interpret the factors as follows. The first factor displayed strong positive associations with strikeouts and home runs for both offense and defense. This interpretation was aided by my knowledge of the prior collinearity between the offensive and defensive home runs, both hit and allowed. And it also had a strong negative association with triples, suggesting that the factor was related to an all-or-nothing approach that heavily featured strikeouts and home runs. The second factor displayed strong positive associations with fielding errors and hits allowed, and strong negative associations with walks taken. This suggests that factor 2 is related to poor base runner prevention for both pitchers and fielders, and an impatient approach at the plate. Factor 3 displayed strong positive associations with walks from both the pitchers and hitters, and no strong negative associations, suggesting that this factor is related to playing games with a lot of walks on both sides. The fourth factor displayed strong positive associations with triples and stolen bases, and a strong negative association with home runs. The errors committed and double plays turned variables were very close to the 0.4 cutoff, suggesting that factor 4 was characteristic of speedy teams that don't hit a lot of home runs but play bad defense. A little counterintuitive, but still interesting. Finally, the fifth factor displays strong positive associations with hits and doubles and no strong negative associations, suggesting that it represents contact hitting without much regard for power. From the factor analysis, we were definitely able to identify underlying factors that related some of the potential explanatory variables together. Unsurprisingly, some of the different variables were related to each other, suggesting that there is a stylistic flavor towards certain team profiles. The term selling out for power in baseball means taking on an increased risk of a strikeout to generate a higher chance of a home run, and it was interesting to see that appear in factor 1. Some of the factor interpretations made more intuitive sense than others based on my familiarity with baseball, but that is unsurprising given the nature of this unsupervised exercise. In this project, I was successfully able to perform clustering of similar baseball teams in this dataset and identify interpretable factor representations of the data as well. The cluster assignments were not amazing, and there was indeed some overlap there. However, it was still a useful exercise to identify that there were some similar teams present in the dataset. The factor analysis provided us with some interesting interpretations of common underlying factors that hint at teams playing certain styles of baseball or having certain shared characteristics, whether that manifests as a power-centric approach that tolerates higher strikeouts for an increased chance of home runs, or as a group that played bad defense and allowed a lot of hits. As the number of factors increased past the 5 or 6 threshold, we started seeing factors without any strong association, suggesting that they were not particularly useful to interpret. There were some issues with data quality and multicollinearity, which definitely had an impact on our analysis. Based on knowledge of certain historical baseball records, some of the observations from the dataset were not possible and hinted at potential data quality problems. Not having many values filled in for times hit by pitch definitely altered the final analysis and likely had an impact on our overall conclusions compared to a world where this was available. However, the exercise was still very useful and provided some strong background knowledge to serve as a jumping-off point for a potential future analysis. The enhanced understanding of this dataset acquired through these analyses would serve as a great starting point for a potential supervised analysis on this dataset, presumably to predict team wins, which was one of the variables in the dataset that we didn't bother using in these analyses. All in all, this was an effective way to learn more about the dataset and gain some valuable background knowledge for additional work in the future relating to baseball data. Thank you for your time, and I hope you have a great rest of your day.